Welcome to the afternoon seminar, which will be by Anatoly Konechny on the orthogonality, catastrophe, and perturbed CFTs, which are not two-dimensional.
No, perturbed d-dimensional. Right, thank you. So I want to start just by kind of very quickly explaining what people call orthogonality catastrophe, because this is a term which was used in the 50s and 60s when people were trying hard to put quantum field theory on a rigorous basis, and they're working on axiomatic and constructive quantum field theory. And this kind of orthogonality catastrophe was a term coined when discussing the meaning of Haag's theorem, which basically, so it was formulated by Haag, but then proved by other people as well. And there, if you consider a perturbation, could be, you can write it Lagrangian quantum field theory. If you start from some free theory and then you include, say, some potential, then standard thing in textbooks is to pass to interaction representation, interaction picture, and that boils down to using what's called Gell-Mann law formula. And in that Gell-Mann law formula, it's normalized in such a way that there is an overlap between the, so if there's some coupling constant lambda here, overlap of the unperturbed theory and perturbed theory vacua. If so, the basic assumption for the existence of interaction picture is that this is not zero. But Haag and other people argued that rigorously that that's not possible. There is no, and the mathematical explanation is that basically you cannot assume that the perturbed theory Hilbert space is unitarily equivalent to the unperturbed theory Hilbert space. So that's sort of the just a historical quick excursion into the term orthogonality catastrophe. This turns out that they are, there's a strong argument, axiomatic argument, that this is zero. And then people have been arguing what to do with it. Of course, all the practitioners of quantum field theory, it never stopped anyone to use interaction picture, to keep computing things and to keep, comparing things to experiment, etc. So it's all somehow works. The result is there. So very briefly, what I'm going to consider perturbed CFT. So where I'll start, well, it will be, okay, not quite the Lagrangian, but okay, schematically, CFT plus interaction, right? So it's in some integral, and Haag's theorem applies at infinite volume, but we're working with finite volume. And this perturbing operator for me will be a scaling operator of dimension delta. And sort of one result, which I hope I definitely plan to explain today, is that when the scaling dimension is greater or equal than d plus 1 over 2, you run into these kind of problems with orthogonality and with the different Fock spaces. You cannot assume that your perturbed theory Hilbert space is still the same as the unperturbed one. So this is like very quickly sort of sketchy formulation of the main result, infinite volume. In this situation, trouble. But I also hope to discuss like how do you do this? The answer is, I think, renormalization. Just, but you have to renormalize not only the coupling in your Hamiltonian or Lagrangian if you have one, but also you have to renormalize the wave functional. So I plan to, I hope to discuss that part as well. So now let me get more concrete and start writing some formulae. So I will first target deriving this, showing you, convincing you how it works. No trouble. Yeah, you can perfectly think that even if you have divergences with the coupling, you can perfectly think that your perturbed theory Hilbert space is the same, and say eigenvectors of the Hamiltonian still sit inside that as normalized vectors.
Slightly relevant, just a little bit less than D.
Yes. Well, I mean the opposite.
Yeah.
The nice situation. Yeah, the more relevant, the better.
Yeah, but if it's only slightly relevant.
No, this is over 2. So this is.
Yeah, but I mean that would include, delta equal D, perhaps. Because that's going to be bigger if D is bigger than 2.
So delta equals D, that's when all hell breaks loose. Yeah, that includes that for sure. This is when we have all loops beta function. The theory is no longer superior normalizable. So yes, that includes this, of course, case. That's the worst.
And you also have lower bound.
Bound on what? Well, I have not used unitarity, but I assume delta is positive. Yeah, no, I assume at least. Okay, I mean, you can of course look when, yeah, this is only relevant when this thing is less or equal D, right? So you were thinking about, yeah, that's sure. Yeah. So, but then what is the dimension? Yeah, so what? 2D greater or equal than 1? Sorry, D is greater or equal than 1. That always holds. This is the dimension, so that's okay, I think. Okay, so, well, conformal perturbation, first simple remark is that if you do it in flat space, so if you're not in finite volume, you run into infrared divergences right away, well, very quickly. I mean, the low orders of perturbation theory can be convergent in the infrared, but since all your correlation functions in flat space, they decay power-like, after some point on, after some number of loops, all integrals will be infrared divergent. That doesn't mean that it's completely useless. There are quantities which are free of infrared divergences, like Wilson OPE coefficients. So you can develop nice conformal perturbation theory for those. And then if you have a strictly relevant perturbation, it is believed that, you can put in all the infrared divergences into one-point functions, which are fully non-perturbative. And then, if you somehow have information about those, you can live in flat space. However, it's obvious that, things are much nicer in the finite volume. So you can think of it at least as a regulator for infrared divergences. But also, if you want a Hamiltonian formalism, then you want a nice discrete Hilbert space. So you'd better have a compact spatial manifold. So I'm going to choose this cylinder, which is a sphere times R. And the first thing we can look at is the following amplitude. So I'm going to draw just like a 2D cylinder, but imagine it's in any number of dimensions. And I'm going to perturb a finite portion of this cylinder. So here I insert dd w, and this finite portion of the cylinder I call M capital T. So it starts from 0, ends at capital T. This is my Euclidean time direction. So I'm in Euclidean time here. And so this is just R e minus 1 cross. So sorry, to be consistent everywhere, I choose 0 here and minus t. Okay. Then we can set up the free energy difference. So we'll denote here the perturbed partition function. So it still comes with this parameter t, can take its logarithm, and the perturbation theory series is well known here. So this is the n copies of my cylinder. And here, because I took the logarithm, I have connected correlation function. So this C means connected. Well, this is a formal perturbation series. I mean, if you can think about it, if you're more mathematically inclined, you have to introduce some regulator. Say I should forbid all the collisions between the operators somehow in the regulator, so it's all a finite quantity, so it's a finite series. Yes? No, I'm saying from a CFT. So V is the scaling operator in the CFT, right, of dimension delta. The only thing. Okay, so here's the definition. So the ordinary one should be it's a sum of all partitions of these endpoint functions, and here is a product over all subsets which belong to the partition. Yeah, I'll just quickly denote it like this. Okay, so this is a recursive definition of what the connected correlation functions are. So you can walk backwards and express connected in terms of the ordinary ones. Mm-hmm. Okay, so so here, so this correlation function is taken in the CFT vacuum. So I can use translation invariance to make one integration, right? Because so there are endpoints here, but because of translation invariance, there is one redundancy. So to take care of translation invariance, it's convenient to fix the ordering. So I can get rid of this 1 over n factorial by fixing the ordering. Okay, and then change variables. So my W1 will be the same as before, but then I have the differences. And then there will be n minus 1 of them now. So effectively, I'm just using translation invariance to put W1 to 0. And then the limits only change, the limits of integration change for tau 1. So I should take the leftmost tau n, and that sets the limits. So for fixed, so these guys are fixed. This is a range of integration. So it's a triviality, but and I hope just to convey. So integrating out W1, we obtain that this log has two terms. One extensive in T and one non-extensive. So for the extensive guy, so because T will come from the limit, right? And then there will be something with containing this guy. So this will be, so if I take T to infinity, then this will be the vacuum energy shift. This is the extensive piece, or you can look at it as a free energy piece, extensive piece. And then there is a new guy, which I call GT. So here, right, what do we do? I'm out of practice with the board. No, I cannot continue. No, what's the strategy? I continue writing here. Okay, so so this first bit, epsilon 0 t lambda minus epsilon 0 t, that's, you can write it as a volume as R of the spatial sphere, and then just these integrals. Okay. And GT is a more interesting guy. Here I kept the ordering, so there I went back to the arbitrary ordering. Here I keep it. So and of course I can again symmetrize this integrated correlation function, and the main point here is that this tau n minus 1 is the minimum of tau 1, tau n minus 1. So these taus, these are the shifted taus. These are not the old taus. I probably should have used a different notation for this kind of shift. So let's put a twiddle on it to be precise. Right, so this tau twiddle k is probably tau k plus 1 minus tau 1. Okay. All right, so we are integrating over psi I, thank you. Over all of them, yeah. Yeah, same as here. Over all of them. Okay, so this quantity is very well known. So this is just the perturbative series for the vacuum energy shift. It comes with the extensive term. This quantity is new. So what I'm going to argue is that if I take now limit, so limit of t goes to infinity, right, of this GT. So why can I do that? I mean, I can do that because I do have here connected correlation functions which fall off at infinity. And even though I do still have this flat infinity in the Euclidean time, the correlation functions, now they decay exponentially. Right? So I introduced the scale r, the size of the radius of my sphere, right? And then I decay exponentially. So I can do that. So the claim is that this quantity, which I'll call, so this quantity I shall call just g. Its meaning is that e to the power g over 2, that's the overlap of the two vacua. So 0 is the CFT vacuum, and this is the perturbed theory vacuum. Yes. Yep. Well, I pinned down the 0. I pinned down the yeah, that's it. This is it. So I did here. I also pinned down the 0. It's still connected, but there's also this strange minimum of distances, a strange looking piece. Okay, so how do I see that this piece measures the overlap of the two vacua. Who's an eraser? Okay, for that, we just have to reinterpret this amplitude, the log of the ratio of the partition functions. We have to rewrite it in the Hamiltonian language. So here, just basically used as the definition of the perturbed theory, this the integrals of correlation functions. But now in the Hamiltonian language, we can insert the partition of unity of states in the perturbed theory, and then this ratio of partition functions can be written in the Hamiltonian form. And here we have the energies, the excited energies. Right, so there is no T here. Should be the T. Ej of lambda minus E0 T. So it's just standard Hamiltonian expression. Then the leading term, as T goes to infinity, it should be the overlap of the vacua, of the two vacua, squared, times the energy shift. So now if I match these asymptotics with that correlation function calculation, I see that, so this piece was e to the g, right? Therefore the overlap, so here there's an arbitrary phase, which I can just fix by hand so that this, this thing holds. Okay. Is this very simple? Sum over, this is an integration. Oh, sorry, I rushed through. Yeah. Well, the zeroth order term is actually 1 and starts with 1. Yeah, so yeah, now this is, I think this is okay now. Yeah.
At this point, at least, is there any difference from what Anderson did for the combo for any impurity problem many years ago? I mean, this expansion, right? All this works.
I don't know.
The same expansion without DFTs.
I have not seen this expression before for the G.
So by which expression do you mean the tau twin?
I haven't seen this formula yet. Okay.
I mean, you perfectly expand the condo partition function. It's exactly like that. That's a Coulomb gas kind of correlator.
So you mean you're interpreting this tau, this insertion tau, as some kind of correlator?
Yeah, because the condo has an extra spin. So it's a spin. So
Sure.
it's an extra spin.
I didn't put in any extra degrees of freedom. I just took my bulk theory and perturbed it. I didn't put on any kind of degrees of freedom at any boundary. I mean, there is a cylinder here. There's a boundary of the cylinder. But I didn't put anything by hand there and didn't integrate out anything. All I did is...
I mean, what I'm saying is, if you take the perturbative expansion of the quantum impurity problem, this is, as far as I recall,
Okay.
original place.
So you're saying this is very general, right? I haven't assumed any. But I actually that's an excellent comment, because I would like to have some kind of pretty picture for this strange sort of series, which involves this kind of, it's a minimum of all of these taus.
Yeah, maybe I forget. Maybe it's not precisely that, but the point is.
Okay.
it's not
Yeah. It would be
short
yes.
years, but then there's
So yeah.
Some additional thing depending
Okay.
on precisely which
So I don't know.
year.
I'd like to have some intuitive picture for what it is, but at this stage,
Okay.
you know, it is
But at
what.
least up to that, it's
what it is.
basically completely general what you're.
Yeah.
What
Mhm.
without, except for the specific form of tau twiddle, it's basically.
Yes. Yes. Okay.
Okay.
Yeah. Good. Okay. So now we can do more. I can actually. So this is an overlap with the vacuum. I'd like to find also a formula for all components. Yeah. Yeah. I didn't put anything, just the vacuum. I put the vacuum. Yes, that's right. I put the CFT vacuum. So now I'm going to put on one end vacuum, and on the other end I want to put the an arbitrary state. So I can look at more general finite amplitude, and then you do similar stuff, and you work out. You can you get a formula for all overlaps, which I can summarize in the following expression. So it's a limit of some, regulated formal vectors. Here I want them regulated. Yes. And then path ordered exponential. Okay, so this formula now summarizes all components of the perturbed vacuum, and one can formally find that the normalization here is chosen such that the norm of the limit is formally 1. And this formula should be compared to the standard Gelman law formula. So in the standard Gelman law, the perturbed theory vacuum is written like this. So there is some adiabatic switching on. We are in the real time, not imaginary time. And we use interaction representation propagator. So this is the standard Gelman law. So basically this U, so I'm working in Euclidean with imaginary time. So this U can be also written as a path ordered exponential. Sorry, here I should remind people that the adiabatic switching on looks like this. So G is the coupling. I should go with lambda. So this is the coupling, and so there's this. So if t is less than 0, that this is the adiabatic switching on exponential. So the analog of this U operator is this path ordered exponential here. I use directly in the Euclidean, and it has a similar form, except for there's an I there. So it's formally a unitary operator. Instead of using epsilon, which is a form of infrared regulator in the standard Gelman law calculation, I'm using capital T. So I'm using this sharp Euclidean cutoff, so it's another kind of regulator. But more substantial difference is actually in the normalization. So the way Gelman law is usually set up is such that here, if the overlap, so Gelman law, normalization is that this overlap is 1. So this in sort of standard quantum mechanics is often called like intermediate normalization, right? But this thing is set up in such a way that the norm of the entire thing is 1. Not the overlap, but the norm. So I have a formally normalized expression. Okay, so this is not the end of this story, because one can do better and get rid of this limit t goes to infinity and write quantities for all overlaps which are free of capital T. Okay, so to do that, I mean, T is still hiding. So why here I have connected correlators? If I expand this p exponential, those things are not connected yet. So I have to do one more thing to extract completely the extensive pieces and then just get rid of them for good. Okay.
Infinite renormalizations sharp cutoff, because in modern language you would call this an RG interface.
Yes, that's right. It's right. So it's all, yes. So all of this is coming. Yeah. It's a formal perturbation series. Like we do in the bulk. We have set up perturbation series. Then we hope we can isolate divergences, renormalize it, and then sum it up. So okay. So that's sort of same style at the moment. But yes, there will be these boundary divergences related to renormalization of the interface. Yeah. Gelman law. So in Gelman law, this 0 lambda vector, so I should call it Gelman law, is normalized in such a way that not the norm is 1, but the overlap is 1. In the formula I derived, this formula, the normalization is different. So I'm comparing my formula, which doesn't have this, which has I mean the formula where the stuff went. Oh, this is, sorry. It got lost. I erased, I think, that formula that the overlap is e to the g over 2. Right? So in my formula, the overlap is e to the g over 2. In Gelman law, it is 1. Okay, so there's one more step to get rid of this infrared limits completely. So I need to introduce the analogs of connected correlators. So for these quantities. So here, yeah, there was a question already. So this is the vacuum. This is not the vacuum, an arbitrary state in the CFT. Okay, so I can set up such amplitudes. And now I can just formally think of it as this operator, when one more operator inserted at infinity, right? And then the usual correlator. And then the connected ones are introduced in the usual way. So if, as a connected n+1 point function. So I v of psi1 dot v of psi n connected. That's again sum over partitions. Partitions of these points now infinity psi1 dot psi n. And here product of everything which is in the partition. So this is the recursive definition of connected things. And here I'm assume, so this only works if the overlap of I with the vacuum is 0. Okay, so this formula works for all states except for the vacuum. But for the vacuum, I already have a nice formula for the overlap. Okay, so to formulate now the entire thing. So this overlap now can be just written as e to the g over 2. Here is the sum minus lambda over n factorial. And here I'm integrating over my cylinder. Already now infinite. And I'm integrating these connected guys. Okay, so here I already took formally the t goes to infinity limit. I got rid of this extensive bit, so it just comes out and cancels. And e to the, so this is the crucial guy, so it multiplies these components as well. So it multiplies basically the entire, the expression for the vector, the entire thing. Okay, so I'm going to now see when do you get divergences here, and that will lead to, if I want to keep norm 1, so these guys will go to 0, all of them. So not just the overlap, but all components in your vacuum. So you can think simply that if you have, if you write some expression in the Hilbert space, especially if you kind of don't look at all of the components, if you truncate, then then you can always make it norm 1. But if in the limit you get something of infinite norm, and you're always keeping it, keep the terms in the of norm 1, then each individual component must go to 0. I don't know if it's making sense. Yeah. Okay, so that's sort of me done with this form kind of Euclidean version of Gelman law, where I get a perturbative expression free of any infrared divergences, order by order of components of the vacuum, perturbed vacuum vector. Okay, so yeah. Yeah, it will be, this exponential will give you the g function of the interface, that thing. Yeah.
Those don't have to be 0, right?
Right. So I should renormalize my interface somehow different. I should properly renormalize it and this, forget about this condition insisting that this norm is 1. Okay. Yeah. So So okay. So now we're looking at the leading term. So this g. I have a formal power series for it, and it starts with 1, and then there's a term g2, and then all the rest of them. So for g2, you can substitute the 2-point function and integrate it. So you get basically some terms from the volume of the sphere and some other factors of pi. And then it doesn't come out as just a combination of gamma functions as the usual sort of conformal perturbation theory integrals, because the integral is a bit more complicated. It's on a sphere. It's not on an infinite space. So the usual tricks like Schwinger parameter, etc., unfortunately don't quite work. But you can still wrap it up into integral of so log x of the hypergeometric function. And here's my arbitrary dimension. And then you can analyze its convergence near 0 and 1. And you find that it converges for delta less than d plus 1 over 2. The what? Yes. No, not inside the log, sorry. Log x is just standing there. Yeah. All right, so that's what you find. So this guy G has since the 2-point function is positive, in this leading term, we integrate it actually with a negative weight. So this divergence will be negative. And you will see that if you keep this factor in front, so if you don't introduce any counter terms, you just regulate it. As you remove regularization, and you are not in this situation, but your delta is greater or equal than d plus 1 over 2, then this guy will go to 0. And this is what you would also see if you're doing on the machine. You're doing, so for, say, for 2 dimensions, for d equals to 2, you have to choose some CFT, and you have to choose a perturbing operator of dimension greater or equal than 3/2. And then basically you can use a truncated conformal space approach to construct your Hamiltonian, then truncate it a certain way to get the finite matrix, diagonalize it, and obtain the vacuum vector. And then you will see that if you start sort of removing the truncation, you allow more and more states, then all of your overlaps, they start going to 0. So, so the first thing, so the threshold is interesting because you get a logarithm. So you get a logarithmic divergence.
This is the UV that
Yes, because these V's were collision. Yeah, exactly. Yeah, they were mildly regulated by the tau, but that extra factor of tau which emerged. Sorry. What? Did I mess up something? Where was G minus 2? I think the overlap is with the plus. I cut 0. It's minus lambda squared. So what sorry, where's limit? Sorry, this was the old formula, the sort of Leggelmann law. I have to find it. What?
That's your formula.
Yes. Right, this was subtracting it. Yes. So this was before, right? So before I massaged it more. I massaged it with introducing this connected part, and when you split it into connected parts, e to the g plus g emerges, and also this guy also gets cancelled. So this turned into plus g over 2 after I rearranged my correlation functions into connected parts. Because the sum, the full correlator's sum, splits it can be represented as a product of connected with V and connected without V. Connected without V, they will give you exactly this and these terms and cancels them. Well, no, is G gets partly cancelled, and the extensive piece completely cancelled.
So it becomes plus G over 2.
Yes. Yeah. Sorry, I did a lot of details, but I didn't mean to do completely like over.
You say it's important that this converges so that that expression doesn't blow up.
Sure. Yeah. So when it blows up, that the first time it happens is when delta equals d plus 1 over 2, and that's for example.
2-point function goes like 1 over r d plus 1.
So, right, because I'm integrating is when one extra factor was this tau, which smooths the divergence a little bit. angular, basically, yes, but that's just, sure, you have to do it. That's why you get this hypergeometric thing.
Don't quite see the difference because I will get an R to the D minus 1 from the angular.
Yeah, we can do the OPE analysis. This is just a calculation. So so one integral over went away by rotation invariance, but another one remains, and that actually produced this F21 for me, and then only one integration remained sort of a long time, which I changed the variable into compact integration from 0 to 1. So what you were expecting, it will be 0? So the second angular integration.
I was expecting some smoother UV divergence.
It is smooth. It is smoother than. So we require this for E0 to converge, right? And so this is smoother. Okay. So, right. So this, incidentally, for example, this logarithmic divergence that happens in d equals to 3 in lambda phi to the 4th theory. Right? So you get this logarithmic divergence, and the counter term, just looking at the dimension. So you have lambda squared. So the counter term looks like you need a boundary counter term, which will live only on the sphere. So it's tau equals 0. Okay, and so the dimensions dimension of lambda squared is 1 over length to the d minus 1. So that fits with switching on this boundary counter term. Yeah. But it's logarithmically running, so which means some kind of ambiguity sets in. You have to choose some scale for that. There are more divergences. At high, if you start cranking up the dimension from this expression, you will also see the leading divergence becomes power-like, but there are subleading logs, and so they will appear at other values like d plus 3 over 2, d plus 5 over 2, subleading logs. To me, it seems like I should be I should start involving the curvature. So if I want some kind of local operator, I should just take the curvature and integrate it and so on, just based on the dimension. I have these things. Okay, so I want to now give some kind of a summary of this stuff so far. So, so this is a new type of divergence, which was not present in the standard. So the standard bulk counter terms will not take care of it. So which I needed for renormalizing the coupling constant and the Lagrangian. So if we leave it untreated, then yes, there are some problems. All your vacuum vector components will be going to 0. So if you do it on the computer, so there are consequences for, say, practical applications. If you're doing Hamiltonian truncation, then you will need to think about this. And also, this serves as some kind of organizing principle. You can, if you think of the perturbed CFTs, then they get, so the UV divergences get more and more involved as you increase the dimension. So essentially, there are two thresholds. So if delta is equal to d over 2, so if you're below it, basically you're dealing with the finite theory, which is so relevant that you don't have UV divergences. Then between d over 2 and d plus 1 over 2, you have only bulk divergences. And then above this threshold, you start also dealing with, I call them boundary divergences, because they need boundary counted terms. And then things get really bad when you arrive at delta equals d, because you start, so you lose, so still you need finitely many primitive counter terms until then. But then from that point on, you will need, so it will be all loops beta function and all loops running of this e to the g. There are other divergences. So this was the overall factor, so I focused on it. But there are even more serious divergences. For example, the components, they start diverging as well, individual components, from that second series. So e to the g over 2 multiplies the whole thing, but there's still a perturbation series for the non-trivial components. So you can analyze, you can find that the second order overlap with, say, primary converges when delta is less than z plus delta I over 2. And at this threshold, this is actually, this will be the bulk divergence. So the divergence is cancelled by bulk counter terms. And this divergence corresponds to the resonance when the OP of V with V produces VI, and so you have here, x to the d. So if you get this resonance, that leading divergence will be cancelled, but then there is this another logarithmic divergence at delta equals this value, which is greater than d plus 1 over 2 I had before, a new log divergence. And that is better be cancelled by a non-trivial operator on the boundary. So the dimensions suggest this counter term when I put phi I corresponding to the primary I on the boundary. So this is again integral over st minus 1 r. So that's more serious for practical purposes, because essentially this implies that in my vacuum vector, the different components start diverging with different speed. So once I had the overall factor, it's not too worrisome. I can live with it, even say in computer simulations. But if my dimension, if I am in this situation, which is even higher, and I happen to have this I, and there's an OP coefficient VVI is not equal to 0, in this situation, I need to introduce this boundary operator, non-trivial operator on the boundary, and that will if I do this, I will rescue my sort of different components of the vacuum vector. Right, so at least I'm running out of time, but I want to mention some, maybe a couple-fold examples. Oh, these are the leading ones. And I know the two-point function. So I can integrate explicitly and get the answer. I can also, three-point function already is like, I can analyze convergence, but the integral is pretty bad. But I'm very general. So the leading divergence will come from the lowest collision. Right? The earliest you can get, so at this stage, when I reach this point, the second order amplitude contains the divergence, but the third and higher, they will be finite. If I start increasing from here, this point on, only second order diverges. When I start increasing the dimension, there will be finitely many terms. It's still super normalizable, there will be finitely many orders of lambda where I have and I can have new divergences. G3 can diverge G4, and so on. So I focused on here because that's the threshold, and that's not going away. Yeah.
The 2 was the 2 in the denominator is the lambda squared. I thought that would go the other way.
2 in the denominator, G over 2.
The d plus 1 over 2. That over 2 comes from the fact you're looking at
No. It just comes in analyzing the divergence of that integral with f to 1. I have that integral with f to 1. And it diverges when it... Yeah, yeah, this is why this is a new divergence. It's not sort of cured by any bulk ones.
you could have like a lambda 4 lambda 4 cosmological constant, right, which would be marginal for a smaller value of the dimension.
In what theory? You think in some kind of particular theory? Yeah, I mean, this is just, this kind of universal threshold. Then in other theories, you can have all sorts of higher divergences, especially if you take this delta higher. If you take this delta higher, you can have other orders diverging as well. Sure, you will have to. If you can analyze and cure all of them, that's great. That will mean you'll have to go to a certain order in perturbation theory. But I'm trying to study some universal properties. So what is interesting here is d equals 1, which is boundary RG flows, so defect RG flows in any number of dimensions in principle. So what counts is only the integration. So here, this threshold merges with that threshold. And you basically only have, dimension 1/2 and dimension 1. So if you have a relevant perturbation, you don't have to worry about this problem at all. So for boundary flows. And this particularly makes it nice, I think, besides the truncated conformal space approach, I think this also affects variational methods. And so for variational method, you want to have a trial state sitting inside your unperturbed theory Hilbert space. So that's quite important. So the one-dimensional flows should be really, relevant flows should be really well suited for variational method, right? So that's one observation here. Yeah, but I can still have divergences. So yeah, when I reach this threshold, like Kondo model, it's a very complicated thing. It's an all loop beta function plus this divergences as well. But yeah, right. So one like old result. I mean, I think, and then I'll stop. Yeah, is it? Okay, just want to connect it to something. I mean, hopefully people seen before. You can consider, so example, you can consider mass perturbation of massless free bosons and fermions. And that is solved by Bogolubov transformation, which schematically looks like this. I have some matrices, capital A and capital B, and so these are massive and massive creation operator, and these are massless. And then it's a well-known mathematical fact that the formal Fock space vacuum has a finite norm if the trace of this product is less than infinity. And yeah, it's a simple calculation. You can, of course, calculate this trace and see that for fermions, trace is finite when d is less than 3, and that matches my threshold. That's the dimension of the perturbing mass operator for fermions. And if you impose this, you see that only dimension 2. This is convergent. And for bosons, this thing converges for d less than 5. And then again, sort of the dimension of the perturbing operator is d minus 2. And if you impose that it's less than d plus 1 over 2, it gives you that. Moreover, I mean, when you analyze, sort of these expressions will be given by some integrals in momentum space, you'll see that the divergent term is exactly proportional to the coupling squared. And it's a very well, I think, known result, this sort of condition for Bogolubov transformations. But I think sort of, I don't know, what was missing in the literature is kind of understanding that this is some local divergence underneath all of this. And therefore, one can set up local renormalization theory, which should be renormalization of the RG interface. And there are some, interesting issues here I'm still working on. So I think I wrote that it's work in progress, but I want to emphasize now again. So that's the good time to stop.
Questions?
Say what's the stumbling block in showing
Oh, I don't think there is a stumbling block. No, I think, no, I mean, so yeah, well, I'd like to understand more sort of the details, how you set up the counter terms. And it looks like part of the story is you just, want to renormalize this interface, right? For example, you can say, I can look at some 2-point function, and I want to make it finite, and then there will be extra divergences when the perturbing operators, they come and collide with the boundary. And these counter terms should be there, but there's a bit more. If I insist on having my vacuum state normalized, so this G thing, actually, it will be almost, so you will remove lots of divergences by these ordinary counter terms. It's like this. Oh, by the way, when I told about this operator guy, I forgot to mention that Simanchik discovered this in G phi to the 4th theory. So he was renormalizing vacuum wave functional in G phi to the 4th, and he discovered that there is a new logarithmic divergence. You need to introduce a boundary counter term, which is phi normal phi on the boundary. And that has logarithmic running. So it enters into Cullen-Simanchik equation and stuff. So it's partly, old story, but I'm not sure how many people sort of remember this Simanchik. Oh, okay. So here we should start with the bulk then. So nobody did in the bulk, like a sort of BPHZ kind of proof that any perturbed conformal field theory, order by order is consistently renormalizable. So I should start, one should start there, just using properties, factorization properties of, I could start, say, with conformal blocks and have, say, finite.
the conformal theory is free? Can you prove the interface is renormalizable in this sense?
Okay, you want some kind of BPHZ version, but say with a free field. I haven't thought of that. I don't know. Perhaps possible. But it seems to me, this is a much wider class of perturbed theories, right? And it seems to be there should be an analog of BPHZ proof, which hinges on the properties of, say, conformal blocks. If your theory has, say, like minimal mole, finitely many primaries, and nice properties of conformal blocks, then order by order, all the it's renormalizable in the sense that all kind of collisions between lower number of operators, which enter into renormalizing your high order, will cancel subdivergences, and what remains is a single collision of all of them. So It feels like they should be, but nobody has done this. But yeah, I don't know. I want to understand sort of how to, at least perturbatively, everything maybe in up to the 4-point function, how everything works together in this case. Because G has, you know, this e to the G over 2, it introduces more counter terms proportional to the identity on the boundary, which keep the norm 1. So they need it for normalization. But I think once this starts diverging, I should abandon insisting on norm 1. I should introduce a new scale in the problem. And perhaps I can just look at this, you know, two interfaces separated by a distance, mu inverse, and say that this is equal to 1. That's my idea of new renormalization condition, right? And then I can follow in the infrared and extract from it a number. So there will be a renormalized overlap, which is some number which accompanies RG flows. And you know, for if you have an RG interface, for example, you know, Gayotto constructed an interface between for the RG flow between the neighboring minimal models. So a few years back, I did a calculation of this factor with Cornelius Schmidt-Collinet for short flows, for short RG flows. And then we plugged in the parameters for the Gayotto, and we got a matching with the exact algebraic value of that G. So, but I don't know what is it in 1D. I have a clue, but I still, because what could it be? And I don't know what is it in 3D, for example. I know on 4D.
Maybe we just comment. So 1 plus 1D with the boundary problems, this has been long solved. This is what Anderson was doing in the 60s.
Okay.
If you look up orthogonality catastrophe.
Okay.
Anderson
Okay.
usually
Okay.
this is exactly what he was doing.
I've been always suspecting this. All of this has been done.
so that's all.
Yeah.
More stuff.
Okay, Anderson, and there's orthogonality catastrophe in the title or somewhere. Okay. Yeah. Okay. But he had a particular concrete model, right?
Yeah, but I mean, but then it was quickly realized there was a whole class of things. Hondo is one of the key ones. There's another called X-ray edge singularity. This is what they were doing. And then, but the point is, because it's 1 plus 1D, well, it's boundary, so it's 0. Well, it's still 1 plus 1D when you're doing the boundary. You can control that expansion. Solve all these renormalization problems just by explicit computation, and you can see how it diverges. Everything works.
Yeah.
Yeah, because you put it in a finite system. Now, if you want to do 1 plus 1D bulk flows, this is what Affleck and Ludwig were doing. So there's this famous paper like 86 or something like that. So what they were doing is looking at the RG equations. You start with a minimal model. Yes, Gayotto did something, but again, long ago, and you can make sense of this expansion at the RG level. Again, so you just explicitly.
I know, but this is different. So even in 1D, so Affleck and Ludwig, that's the overlap of the, you know, boundary state. So this is in the closed channel.
If I said Affleck and Ludwig, I didn't mean that. Cardy and Ludwig, actually, Ludwig and Cardy. It's when Andreas was a grad student.
Sure. I mean, you mean, yeah, there is a perturbative formula. Yeah, sure, for short flows.
Perturbative formula. You write that series that you that's the stuff. And then you can do the RG with that.
But yes, but this is different. This is in 1D, but this is different. I'm on a strip, and I'm perturbing on half the strip. I'm perturbing like this. This is my.
Well, that's the 0 plus 1. The things Anderson was doing, and then you can rephrase using boundary conformal field theory. So these are boundary condition changing operators. So again, there's a lot of stuff in the 90s where people worked out many explicit cases. And these things are all boundary conformal field theory. Now, in higher dimensions, I don't think anybody's worked it out. So that's probably stuff. But at least you can see how it all goes through. I'll give you the buzzwords.
Sure. Yeah, that sounds good. Great. I suspected, you know, that nothing is new under the sun. Yeah.
It's a silly conceptual question, but if I fix a scale lambda,
Yeah.
the computation we did, for example, with brought I kept vacuum tells us at scale lambda what is the perturbative vacuum in this RG scale theory, right?
Yeah.
If I at minus infinity prepared another state J, will this computation tell me what J goes to?
Okay. So you want, because I looked at situation when, say, yeah, so it matters where you put it. So then the picture, because, you know, there's also Gelman law formula for excited states, right? And that thing is plagued by infrared divergences. So if you read Klassen and Meltzer, so if you do, yeah, so because there, it's, see, if this calculation, if I did it on a disk, right, then, so what I was doing is, you know, vacuum here, and then on the boundary, some state, well, at infinity, but I'm only integrating here, so I'm never hitting the state. Yeah. But you can, if you put I here, then there will be, so it will look like a UV divergence on the disk. So you know, Klassen and Meltzer, they discuss this, but I don't have a good understanding why this infrared divergence is there. So, but this is related to it will be like excited, not the vacuum of perturbed theory, but the excited state of the perturbed theory.
Even though it's e to the minus infinity h, right?
This will come from subleading terms because I isolated the leading one. When you start isolating subleadings, you'll get formally perturbation series for excited states.
So if we could regularize this divergence,
yeah.
does that tell us about, I guess, the spectrum of lower energy operators in the perturbed theory, in the RG, half RG scale theory?
Well, if you believe that this all, I mean, because these levels, they can start crossing, and then this, because there's, you know, perturbation theory will only will have a very small radius of convergence. But in principle, yes, that should give you the excited states with the excited state spectrum. Well, I have to understand how to renormalize the stuff to get the IR first, you know, with the. Well, you will get some conformal interface, right? That's the idea. After you renormalize it, go to lambda goes to infinity, you'll get a conformal, specific conformal interface, which is called RG interface, between the UV and IR fixed points, right? Which has, for example, it has a G factor, and it's an interesting quantity. It's a specific, because it's a specific conformal interface, which came from that RG flow. So I don't know if, I think it might be some interesting properties of this G factor. Well, in this Gayota case, for example, you can find it. Yeah, it's an algebraic expression.
Take one RG flow, there are multiple RG interfaces. There is not the unique one. Because you can always do turn on some partial operator on the boundary, which is localized, no?
Sure, but presumably one per flow, no?
So you fix the bulk.
I fixed the bulk flow?
So you turn on some,
yeah.
Then you can still turn on some IX perturbation on the boundary.
Well, if you don't do it by hand, then
how can you know by hand and not? Because when you renormalize, you will get terms on the boundary. There is no well-defined notion of not doing anything. I just wonder if this is economical choice for.
I'm not sure, but I think there's some kind of physics is hiding here. So it must signify something that if you cannot, I mean, okay.
If you choose a scheme, you get some interface. But
yeah, I mean, especially if you're running some logarithms, then you should be on the boundary. Then yeah, there's ambiguity. So what does that mean? I don't have an idea, a good yet. Yeah.
If there are no more questions, thank you very much.